To perform the Dirac belt trick, you'll need two things. One, a belt. And two, a large book. The book is to keep one end of the belt in place, while the other moves around. To begin, take the free end of the belt and turn it by 360 degrees. You will now see a twist in the belt. The goal is to find a way to take out this twist. What makes this interesting is that you're not allowed to rotate either end of the belt, so you can't just directly undo the twist. However, you are allowed to move both ends around in space, as long as you don't turn them while doing so. Now, you have to try this for yourself to be convinced, but no matter what you do, you won't be able to undo the twist in the belt. So that was a big failure. However, in the beginning, instead of twisting the belt by 360 degrees, what if we instead twisted it by 720 degrees, which is 2 full rotations? Can we undo the twists now? Well, watch this. Amazing! We can't undo a 360-degree twist, but we can undo a 720-degree twist. That's the Dirac belt trick. Paul Dirac, one of the greatest physicists of all time, invented this trick in order to help explain to his students the bizarre nature of quantum spin 1/2 particles, such as electrons and protons. An older version of this trick was popularized in the book Riddles of the Sphinx and Other Mathematical Puzzle Tales by Martin Gardner. For this older trick, the first step is to put your belt back on. Then get a pair of scissors and 2 pieces of string about 10 feet long. Thread the strings through the holes in the scissors and tie off the ends in 2 loops. Now, step on the 2 loops of string and hold the scissors right in front of you straight up. Then, rotate the scissors around by 720 degrees. Once again, you can take out the twist in the strings by moving the pair of scissors without rotating them. But this is sort of dumb, so let's just stick with the belt. Anyway, what does any of this have to do with quantum mechanics? Well, if you take a normal object, like this soup can, and rotate it 360 degrees, it'll end up exactly how it started. But now let's say you have an electron. We'll paint a little plus sign on it so we can see how it's oriented. Let's see what happens when we rotate this electron by 360 degrees. What? What happened to the plus sign? All I see is a stupid minus sign. Well, let's keep rotating it and see if that helps. Ah, look, it's the plus sign again. So we can see that when we rotate an electron by 360 degrees, it doesn't return to its original state, but rather a negated version of its original state. However, when we rotate it by 720 degrees, then we get back the original state. This is the property of the electron that the Dirac belt trick attempts to explain. Now at this point, you may be saying, wait, a 360-degree rotation is a 360-degree rotation. You can't say it's only a half. Well, in order to explain this trick more precisely, I'm going to have to introduce some concepts from the branches of mathematics known as group theory and topology, which will take some time. Having said that, I think it's well worth the effort, because the story of the Dirac belt trick is, in my opinion, one of the most wonderful and fundamental in all of physics. Imagine you wanted to rotate this snowman. You would have to specify 2 things. 1, an axis of rotation, and 2, an angle of rotation. Now, we could rotate any object we want, and admittedly this snowman is a little silly. So let's instead use these coordinate axes. We can once again choose an axis, and an angle to rotate it by. Throughout this video, whenever I rotate these coordinate axes, I'll always include the ghostly image of its original orientation. Now, from here on out, let's always measure angles using radians instead of degrees. So for instance, pi over 2 radians is 90 degrees, pi radians is 180 degrees, 2 pi radians is 360 degrees, and 4 pi radians is 720 degrees. Anyway, to recap, you can specify a rotation with two pieces of information. 1, an axis, and 2, an angle. We'll define the rotation to always go in the counterclockwise direction around the axis, in accordance with the standard right-hand rule, which says that if you point your thumb in the direction of the axis, then you rotate in the same direction that your fingers are curling. Now, let's package these two pieces of information together in a different way. Instead of using an axis and an angle, let's use a single vector, which points in the direction of the axis, but has the length of the angle theta measured in radians. So, using this, how can we understand what the space of all rotations is? Abstractly, the space of rotations is a set, and individual points contained in the set each correspond to one rotation. Concretely, we can picture the space of rotations as follows. Here we have a three-dimensional ball with a radius of pi. Now consider a point contained in this ball. This point corresponds to a rotation, namely the one given by the vector, which has its base at the center of the ball and its tip on the point itself. This vector will have a length ranging from 0 to pi because the ball itself has a radius of pi. Remember, the direction of this vector corresponds to the axis of rotation and its length corresponds to the angle of rotation. To let you soak this in, I'm going to show the vector in the space of rotations on the right and the rotation it corresponds to on the left. Now, there's actually something kind of funny about the space of rotations. Notice that if you rotate around an axis by exactly pi radians in the clockwise direction, the result is exactly the same as if you had rotated by pi radians in the counterclockwise direction. Therefore, this means that a point on the boundary of our ball corresponds to the exact same rotation as the antipodal point on the other side of the boundary. So, we can have a point in the space of rotations go out to the boundary and come back out the other side. While it looks like the point has jumped discontinuously, this is actually just an artifact of our visualization. So, it's actually not quite correct to say that the space of rotations is a ball of radius pi. We also have to include this extra stipulation, which says that antipodal points on the boundary of this ball are equivalent to each other. Let's now give a summary of part 1. It takes two pieces of information to specify a rotation, an axis and an angle. Alternatively, we can use a vector, which points in the direction of the axis and has the length of the angle. We can visualize the space of rotations as a ball of radius pi, where each point in the ball is one rotation. We must identify antipodal points on the boundary of the ball, because clockwise and counterclockwise rotations around an axis by 180 degrees are really the same. Now that we understand the space of rotations, let's think about paths through the space of rotations. Here is an example of a path. It's sort of like a monorail, with a point going around it in one direction. Here, I've displayed the point going around the path alongside the rotation it corresponds to. Enter the belt. If you think about it, a belt is a lot like a path because it has a start point and an end point. As we'll see, it turns out that a belt does indeed correspond to a path through the space of rotations. Here's how. Choose a point along the belt. Now have the x-axis point along the length of the belt, the y-axis point perpendicular to the belt, and the z-axis point along the width of the belt. Now, as we move down the belt, our axes will change accordingly. Because every orientation of these axes corresponds to a rotation, we can see that the belt really does trace out a path in the space of rotations. Let's look at some concrete examples. Here is a path that rotates around the x-axis by an ever-increasing angle. Now let's do the same thing around the y-axis. And here's a version around the z-axis. Here's a more arbitrary shaped path. This looks kind of messed up though. Okay, this one is important. This is the trivial path, the path that just stays right at the center of the ball. Note that the belt corresponding to the trivial path is completely straight. Okay, now let's talk about the belt trick again. Remember what I said the rules of the belt trick are? What makes this interesting is that you're not allowed to rotate either end of the belt, so you can't just directly undo the twist. However, you are allowed to move both ends around in space, as long as you don't turn them while doing so. What does it mean that you can't rotate the ends of the belt? Well, let's look at this path. Notice that it starts and ends at the middle. That means that the axes start and end completely unrotated. But let's look at what happens when we change the endpoint of the path. Notice that if the path doesn't end at the same place it starts, then the final configuration of the axes won't be unrotated. Therefore, our stipulation that you can't rotate the end of the belt means that our path in rotation space must end at the same place that it begins. Now, what was the goal of the belt trick? The goal is to find a way to take out this twist. Remember that a perfectly straight belt with no twist in it corresponds to the trivial path. That means that making the belt straight corresponds to contracting the entire path down to a point. Now, for the path we have here, that's very easy to do. However, let's look at the belt with a 2π twist in it. Remember, this was the path we weren't able to undo at the beginning. And indeed, no matter how hard you try, you won't be able to contract this path. Intuitively, this is because the 2 points on the boundary are actually the same point. But if we wanted to contract this path, we'd somehow have to bring these 2 points next to each other. But we can't do that because they always have to remain antipodal. Now, what about the path with a 4π twist in it? Let's separate out the two strands of this path a little, just so we can get a better look at it. Now remember, earlier I was able to get the twist out of this belt. So let's see what that looks like here. I know that was a lot to take in, so let's look over this a bit slower. Here is the path corresponding to a 4π twist. Here, I've labeled the two pairs of antipodal points. For instance, the 2 points labeled A are really just two manifestations of the same point. Now, let's watch how this path can be contracted. Did you see that? Let's look at it again. Notice how the points A and B are approaching each other, which allows one part of the path to be pulled through the boundary and come out the other side. Pretty neat, right? Here's another way to understand how this path can be contracted. This time, I've kept the path straight instead of curved and colored the two different branches slightly different shades of gray. Let's see how these paths through the space of rotations act on our snowman at different stages of the contraction. Notice that there are essentially two rotations going on, which I've labeled 1 and 2. The contraction works by making the axes go from being parallel to anti-parallel, and then decreasing their respective angles of rotation. So let's give a summary of part 2. Each configuration of the belt corresponds to a path through the space of rotations. The trivial path corresponds to a perfectly straight belt. Some paths can be contracted to a single point without having to move their start point or their end point. The Dirac belt trick is a demonstration of the fact that the path corresponding to a 2π twist can't be contracted to the trivial path, while the path corresponding to a 4π twist can. Allow me to introduce some notation. This expression should be read as G is an element of G. That is, the lowercase g is one element of the set named uppercase G. With that out of the way, let's talk about groups. The word group in mathematics has a very specific meaning. Namely, a group is a set with an operation. More specifically, there are 4 rules that this operation must satisfy. The first rule is that if G1 and G2 are elements of the set G, then G1 plus G2 must also be an element of the set G. Here, we're denoting our operation with the plus symbol. We could have used a number of other symbols, but let's stick with this. The second rule is that there must be some element of the group, which we call id, which is short for identity, such that for any other element of the group G, G plus id is equal to G. The third rule is that if you add G1 and G2 together and then add it to G3, the result will be the same as if you added G1 to the sum of G2 and G3. The fourth rule is that for any element G, there must be some other element, which we'll call negative G, such that G plus negative G is equal to the identity. Here, negative G is called the inverse of G. These four rules are the exact rigorous definition for what mathematicians call a group. Now, this is all a bit abstract. What's an example of a group? Well, one example is the set of rotations. Take, for instance, the rotation around the x-axis by pi and the rotation around the y-axis by pi. How do we add these together? Well, for rotations, plus just means that we do the first rotation first and the second rotation second. So to add these together, first let's rotate around the x-axis by pi, and then let's rotate around the y-axis by pi. Now, notice that this final rotation is exactly the same as if we had just rotated around the z-axis by pi. So, hopefully you can see how you can add two rotations together and get a third one. What about the identity element? Which rotation corresponds to id? Well, that'll just be the trivial rotation, the rotation where you don't do anything. What about inverses? How do we invert a rotation? Well, if a rotation involves rotating around some axis in the counterclockwise direction, then we can undo it just by rotating in the clockwise direction. So we can see that every rotation does indeed have an inverse. So that wraps up the explanation for how rotations form a mathematical group. This is a good opportunity for me to talk about matrices. Let's write the actual mathematical formula for the rotation around the x-axis by an angle of theta. We express the rotation as a transformation on a position vector. We can also write this as a 3x3 matrix acting on the original vector. To explain what distinguishes rotation matrices from any old arbitrary matrix, we have to discuss the inner product. Say you have two three-dimensional vectors r1 and r2. The inner product of r1 with r2, which can also be written as r1 transpose times r2, is equal to the sum of the products of their components. Geometrically, the inner product of two vectors is just the product of the lengths of the vectors times the cosine of the angle between them. Now, notice that rotations preserve both lengths and relative angles. This means that if you rotate both vectors together, their inner product won't change. In other words, if we denote the rotation matrix with the letter uppercase R, then the inner product of uppercase R times R1 and uppercase R times R2 is equal to the inner product of R1 with R2. For this equation to hold for any choice of position vectors, we need for the transpose of the rotation matrix times itself to be equal to the identity matrix. When we have this condition, we say that the matrix is orthogonal. So we see that a matrix must be orthogonal if it represents a rotation. Now, we call the group of all rotation matrices SO3. Here, the 3 just refers to the fact that the matrices are all three-dimensional, the O stands for orthogonal, and the S stands for special, which means that all the matrices have determinant 1. This is just because we don't want any matrices that would flip the orientation of our axes and have determinant -1, but let's not get into that. So from here on out, whenever I say SO3, remember that I'm talking about the group of all rotations of three-dimensional space. One of the nice things about group theory is that, because the definition of a group is so general, it applies in many different situations. Here is another completely different example of a group. First, begin by choosing any topological space. For example, here is the two-dimensional torus, which we call T2. Note that this torus is hollow and isn't filled in. Next, choose one arbitrary point on the torus, which we will call the base point. Consider a path on the torus that starts and ends at this base point. Remember that you can imagine the path like a little monorail track, with the train going around in one direction. Importantly, the path is directed, so if the train were to go around in the other direction, we would consider that a distinct path. Furthermore, we'll consider any two paths to be the same if they can be continuously deformed into one another. Finally, we define pi1 of T2, which we call the fundamental group of the torus, to be the set of all paths which start and end at the base point. Now, even though we used the explicit example of the torus, every topological space has its own associated fundamental group. Now, you may be asking, wait, how can we add two paths together? To answer that, let's look at a different topological space. Here we have a two-dimensional disk with two holes cut out of it. Now let's choose an arbitrary base point, as well as two paths P1 and P2. Here is our little train going around the first path P1, and here it is going around the second path P2. Now, to define the path P1 plus P2, we just have the train go around P1 and then go around P2. We can continuously deform this path to get a better look at it. Alright, so what then is the inverse of a path? Well, if here we have a path P, where the train goes around in one direction, then negative P is the path where the train goes around in the other direction. The path P plus negative P can always be deformed to the trivial path, which is the identity element of the group. So now that we know what the fundamental group is, let me ask you a question. What is the fundamental group of SO3? Here we have a bit of groupception, because I'm asking, what is the fundamental group of a group? Well, here's SO3. Remember, this is just our old friend, the space of rotations. I've put the base point right in the center. Now, here is the only non-trivial path in SO3, corresponding to the 2 pi twist. If we add this path to itself, we get the 4 pi twist, which can be contracted to the identity. Therefore, P plus P equals id. We could also rephrase this as P equals negative P, which is just because P can be continuously deformed into its inverse. Therefore, the fundamental group of SO3 only has 2 elements. Here is the full table for how you can add these 2 elements together. This is the full description for the fundamental group of SO3. Now, if we symbolically replace id with 0 and p with 1, then this table begins to look a little familiar. Specifically, we can see that the fundamental group of SO3 is just the integers modulo 2, also known as z mod 2. Think about all of the beautiful mathematics summed up in this equation. The whole Dirac belt trick is just a demonstration of the fact that the fundamental group of the space of rotations is z mod 2. Now, if you'll indulge me for a moment, I'd like to talk about what makes mathematics so non-trivial. SO3 is a good example of the kind of object you see in math. You can think of it as a group, and you can think of it as a topological space. Therefore, we can study it using group theory, or we can study it using topology. Often in mathematics, you start by thinking about an object in one way, and then discover you can think about it in a completely different way. And, crucially, all the different ways to think about an object interact with each other. So, the group theory has implications for the topology, and the topology has implications for the group theory. Let's give a summary of Part 3. A group is a set with an operation that satisfies a handful of rules. The set of rotations forms a group. Rotations can be expressed using matrices, and the group of rotation matrices is denoted SO3. Every topological space has a group associated with it, called its fundamental group, which is the set of paths which start and end at a base point. The fundamental group of SO3 is Z mod 2. It's finally time to discuss spin in quantum mechanics. You're probably used to thinking of vectors with an x, y, and z component. Normally, we'd say that vectors are elements of the set R3 because they're comprised of 3 real numbers. However, quantum spin vectors are a little different. They're instead comprised of 2 complex numbers, where here alpha and beta are the complex numbers, and thus we say that they are elements of the set C2. Remember that a complex number can be written as a plus bi, where a is the real part and b is the imaginary part. We can also write it as r times e to the I theta using Euler's formula to express it in terms of a magnitude r and an angle theta. The other thing about complex numbers is that they can be quote-unquote conjugated. So, for instance, the conjugate of alpha would be a minus bi. Finally, the absolute value squared of a complex number is just the number times its conjugate, which is equal to a squared plus b squared, also known as r squared. Now, what do these complex numbers correspond to in the physical world? Well, say you had an electron whose spin vector had the components of alpha and beta. If you measure the direction of the electron's spin along the z-axis, then the probability that you find it to be spin up will be the absolute value of alpha squared. Meanwhile, the probability that you find it to be spin down will be the absolute value of beta squared. So for instance, the state with components 1 and 0 will be measured to be spin up 100% of the time, while the state with components 0 and 1 will be measured to be spin down 100% of the time. Notice that, because all probabilities must sum to 1, the absolute value of alpha squared plus the absolute value of beta squared must be equal to 1. Now, as we've discussed previously, vectors in R3 have an inner product where you take the transpose of one vector and multiply it by the other. Quantum spin vectors, however, have an inner product where you take the conjugate transpose of one vector and then multiply it by the other. Just to be clear, in order to take the conjugate transpose of a spin vector, you just complex conjugate the components and turn the column vector into a row vector. Now, you can use this inner product in order to extract the components of these spin vectors. For instance, the inner product of 1, 0 with alpha beta is just alpha. Likewise, the inner product of 0, 1 with alpha beta is just beta. Therefore, the probability to measure an electron to be spin up with respect to the z-axis is the absolute value squared of the inner product of the spin up state with alpha beta. Likewise, the probability to be spin down with respect to the z-axis is the absolute value squared of the inner product of the spin down state with alpha beta. Now, there's nothing fundamentally special about the z-axis. Here, I'll write the spin up and down states with respect to the x-axis and y-axis as well. So, the probability of a state to be, say, measured spin down along the y-axis will be the absolute value squared of the inner product of the spin down y state with alpha beta. And likewise, you would have the same thing for being, say, spin up along the x-axis or what have you. So, whereas the inner product of position vectors is used to find lengths and angles, the inner product of our complex two-dimensional spin vectors is used to find the probabilities of measurements. Now, we can also use the inner product to re-express another equation that we've seen. Remember that the condition that probabilities must sum to 1 implies that the absolute value of alpha squared plus the absolute value of beta squared must be equal to 1. This is equivalent to saying that the inner product of a spin vector with itself must be equal to 1. When we have this condition, we say that our spin vector is properly normalized, or that we have a physical state. Now let's talk about rotations. As we discussed earlier, rotations act on vectors as 3x3 matrices. In order to rotate a spin vector, however, we'll instead have to use a 2x2 matrix with complex entries. We'll label this matrix with the letter U. Remember that our rotation matrix needed to satisfy the condition that the transpose of the matrix times the matrix itself must be equal to the identity. What is the analogous condition that this new matrix U must satisfy? First off, rotating a spin vector shouldn't change the inner product of it with itself, because if that starts off as 1, then it should remain 1 after being rotated. In order for this to hold, we must have that the conjugate transpose of U times U is equal to the identity matrix. When we have this condition, we say that U is a unitary matrix. Now, aside from being unitary, there's one other slightly technical condition that we need to put on U. First, note that the spin vectors with the components of alpha beta and e to the I theta alpha, e to the I theta beta have no observable differences. So, for example, when calculating the probability that the second state is spin up along the z-axis, the e to the I theta makes no difference in the final answer, because you're just taking the absolute value squared of that inner product. Physicists tend to call this factor of e to the I theta a phase. Anyway, this implies that the matrix U and e to the I theta times U correspond to the exact same transformation. Therefore, to get rid of this redundancy, we can choose for the determinant of U to be equal to 1. Finally, we denote the set of all such matrices U that satisfy these conditions as SU2. The 2 refers to the fact that the matrices are two-dimensional, the U refers to the fact that they're unitary, and the S stands for special, which means that the matrices have determinant 1. So, to summarize part 4, quantum spin states are vectors in C2. The inner product of spin vectors involves taking the conjugate transpose of one vector and multiplying it by the second one. There are states which are always spin up or spin down when measured with respect to certain directions in space. The probability that a state will be spin up in some direction will be the absolute value squared of its inner product with the spin up vector. In order to rotate a spin state, you must act on it by a matrix U in SU2. Earlier, we got acquainted with SO3 as a topological space. So, what about SU2? Well, first let's write the 2x2 matrix U and call its 4 entries A, B, C, and D. Now, remember that U conjugate transpose times U must be equal to the identity matrix. This is equivalent to saying that U conjugate transpose must be equal to U inverse. If we write out this equation explicitly and use the fact that the determinant of U is equal to 1, then after staring at this for a bit, we realize that D must be equal to the conjugate of A, and C must be equal to minus the conjugate of B. Plugging these equations back in, we see that U must have the entries of A, B, negative B conjugate, and A conjugate. Now, notice that the determinant of this matrix is equal to the absolute value of A squared plus the absolute value of B squared. If we write A equals X plus IY and B equals Z plus IW, then the condition that this matrix has determinant 1 becomes X squared plus Y squared plus Z squared plus W squared equals 1. So this is all just to say that a completely general SU2 matrix can be given by 4 real numbers x, y, z, and w, such that x squared plus y squared plus z squared plus w squared equals 1. This is the equation for something called the 3-sphere, which we denote S3. How do we picture this 3-sphere? Well, you might be familiar with the 2-sphere, which is given by the equation x squared plus y squared plus z squared equals 1. The 2-sphere, which is hollow much like a beach ball, can be embedded in 3-dimensional space, which allows us to easily visualize it. The 3-sphere, on the other hand, is embedded in 4-dimensional space, which makes it much harder to picture. However, there is something we can do. Let's look again at the 2-sphere. You can divide it into 2 halves along the equator. You can then cut the sphere, flatten out the 2 pieces, and get 2 disks. These disks can be thought of as the set of points with x squared plus y squared less than or equal to 1 in the 2D plane. Anyway, let's refer to these disks as sheets. Here's a side-by-side view of the sphere and its 2 sheets. We can see what it looks like for a point to move around on the sphere from the perspective of the sheets. Notice that when the point hits the boundary of one sheet, it emerges on the other sheet. Therefore, we can see that the 2-sphere is equivalent to 2 different disks glued along their boundary. Now we can return to the 3-sphere. By direct analogy, the 3-sphere can be pictured as 2 solid balls which are glued together along their boundary. If a point hits the boundary of one ball, it will emerge on the other. Once again, we will refer to each ball as a sheet. So, how is this 3-sphere related to SO3? Well, to discuss that, I'll need to introduce the concept of a covering space. Here I have an example of a covering space and a base space. In this example, the base space is just a circle, and the covering space is also a circle, but it's been sort of doubled over on itself. Every point in the covering space can be projected down to a point in the base space. In this example, the projection map is a 2-to-1 function. But instead, what if we want to take a point in the base space and lift it to a point in the covering space? Well, now there are 2 possible choices for a point we could lift it to. Let's just choose the bottom point. Now let's see what happens if we move the point in the base space around in a loop and then bring it back to its original position. Interesting. So even though we initially decided to lift to the bottom choice, when we moved around in a loop, we were forced to end up with the top choice. Therefore, when we try to lift paths from the base space to the covering space, sometimes the start point and the end point of the path won't be the same in the covering space, even though they were the same in the base space. Now we are finally able to describe the relationship between SU2 and SO3. SU2 is the covering space of SO3. Just as in our example, this is a 2-to-1 covering, which we call a double cover. Just to get acquainted, let's see what happens when we move around a point in the base space. Now let's see what happens when we try to lift the path corresponding to the 2π twist. Notice that in the covering space SU2, the start point of the path is different from the end point of the path. Interestingly, you could use this fact to rigorously prove that the 2π twist is non-contractible in SO3. The proof follows by contradiction. If you could contract the path in SO3 to the trivial path, then you could also continuously lift the quote-unquote movie of the contraction to the covering space. This would then get you a contraction of the lifted path as well. However, because the start point in the covering space is different from the end point in the covering space, and because the start point and end point will always stay anchored in their positions during this movie, then clearly we can't contract the path in the covering space. Therefore, the path in the base space must be non-contractible as well, which is exactly what we wanted to prove. Actually, this proof is just one aspect of a more general phenomenon where non-contractible paths in a base space lift to paths which start and end at different points in a covering space. To finish up this part of the video, let me just show you how the 4π twist can be contracted just for kicks. Let's now give a summary of part 5. SU2 is equal to S3 as a topological space. You can picture S3 as two balls glued along their boundaries, which you could also think of as the equator. SU2 is a double cover of SO3. If you lift the path corresponding to the 2π twist in SO3 to SU2, then the start point and the end point of the path will not be the same. This fact can be used to prove that the 2π twist is non-contractible in SO3. At the start of this video, I said that rotating an electron 360 degrees puts it in a negated version of its original state. Let's now synthesize all the math we've learned in order to understand how this statement actually makes sense. The group which acts on C2 spin vectors is SU2. Therefore, to rotate an electron, we must lift a path from SO3 to SU2. SU2 is a double cover of SO3, and the 2π twist ends up at a different element of SU2 than it started. More specifically, if we start the lifted path at the identity matrix, then it'll end up at negative the identity matrix. However, the 4π twist does end where it starts in SU2. Therefore, rotating an electron by 2π negates its spin vector, while rotating it by 4π returns it to its original state. So that completes the explanation. Just to write down some explicit equations, let me explain how to find the SO3 rotation matrix corresponding to a matrix in SU2. Start by taking a position vector r equals xyz and convert it into the following 2x2 matrix r dot the Pauli matrices, which is just x times the first Pauli matrix plus y times the second Pauli matrix plus z times the third Pauli matrix. This is actually the most general form for a traceless self-adjoint 2x2 matrix. Furthermore, the determinant of this matrix is equal to x squared plus y squared plus z squared, which is just the length squared of r. If we multiply this matrix by u on the left and the conjugate transpose of u on the right, the overall matrix will still be traceless and self-adjoint. Furthermore, its determinant will be unchanged. Therefore, we can write this new matrix as a new position vector, which we call r prime, dotted with the Pauli matrices. Because r and r prime must have the same length, r prime must just be a rotated version of r. So the rotation matrix uppercase R is just whatever 3x3 matrix satisfies the equation r prime equals uppercase R times r. This is how you convert an SU2 matrix U into an SO3 matrix R. Now notice that U and negative U map to the exact same rotation. This is how we can see that SU2 really is a double cover of SO3. Finally, I should just mention that there's this really useful explicit formula for the SU2 matrix U corresponding to a rotation given an axis n hat and an angle of rotation theta. Namely, U equals cosine of theta over 2 times the identity matrix plus sine of theta over 2 times negative I n hat dot the Pauli matrices. Notice that if we plug in theta equals 2 pi, then U equals negative the identity matrix, meaning a 2 pi rotation does negate the spin vector of an electron. We can also write this using matrix exponentiation, but let's not get into that. Oof! Glad I got that all off my chest. Now, there are a few things you're probably wondering about. First off, how do you actually rotate an electron? Clearly, you can't just pick it up and rotate it like it's a tennis ball. There are two ways to answer this question. The first is that you can think of a rotation as the result of changing reference frames. For example, say you have your electron, put it on a table, and put that table in a room. If you then walk around the electron and continuously describe its quantum spin state using your own reference frame, then when you've finished walking 2 pi radians around it, the state of the electron will be negated. Now, that's all fine and good, but there's also a more concrete way to rotate an electron. You see, an electron's spin will create an angular momentum vector which points in some direction. If you then expose this electron to an external magnetic field, it'll cause the angular momentum vector to rotate around the magnetic field vector in a process known as Larmor precession. Therefore, you can use magnetic fields to rotate electrons. Here's something else you might be wondering. Is there any way we could experimentally detect the minus sign which comes from a 2 pi rotation? Amazingly, the answer is yes. Here's how. First, take your electron and then put it in a quantum superposition at 2 different locations. Then, subject one of them to a magnetic field, rotating it by 2 pi radians, inducing the minus sign. Finally, recombine the electrons. In the end, you'll find interference effects stemming from the minus sign. This exact thing has actually already been done with neutrons. Look up neutron interferometry for more details. So, way back, when I said that an overall phase has no observable consequences, I was being a bit imprecise. You can detect overall phases in quantum mechanics, but only if you make superpositions and create interference experiments. Here's something else I wanted to tell you about. Real projective space. If you take the 2 sphere and identify antipodal points as the same point, you create a topological space known as RP2, or two-dimensional real projective space. To reiterate, every pair of antipodal points on the 2-sphere is just one point in RP2. We can write this in the language of equivalence relations by saying that RP2 is S2 modulo the equivalence relation that the point xyz is the same as -x, -y, -z. Now, this construction directly extends to the 3-sphere, so RP3 is just S3 modulo the equivalence relation that antipodal points on the 3-sphere are identified with each other. The relevance this has for us is that, topologically, SO3 is RP3. This goes hand in hand with SU2 being S3 and gives us another way to understand how SU2 is the double cover of SO3. On the subject of this covering space business, let me point out that while the fundamental group of SO3 is Z mod 2, the fundamental group of SU2 is the trivial group, the group with only one element, which is because all paths can be contracted on the 3-sphere. Note that the fundamental group of SO3 then has twice the number of elements as the fundamental group of SU2. This fact is intimately related to the fact that SU2 is a double cover of SO3 and not, say, a triple cover. If this stuff intrigues you, you should probably go learn some algebraic topology. One other thing I wanted to mention is the hop vibration. Okay, I've mentioned it. The ancient philosophers, Euclid, Plato, etc., knew that the essence of the universe was based on mathematics. But they didn't know which mathematical objects it was based on. Rather than, say, Platonic solids or triangles, the real building blocks of the universe are things like groups, vector spaces, stuff like that. So, it appears that nature is far more subtle and creative than we humans, because not only did she make these bizarre spin 1/2 objects, she made a whole universe out of them. But, strangely, even nature isn't free to do whatever she wants. She is constrained, and constrained very severely, by the laws of mathematics. That non-contractible path in SO3 is simply there no matter what. So, while nature could devise a spin 1/2 particle, she could never devise, say, a spin 1/3 particle, because the fundamental group of SO3 is Z mod 2 and not Z mod 3. So, while nature is creative, that creativity can only exist within some very rigid, and maybe even tautological bounds. So, when we study physics and mathematics today, we still do, in the end, get that same ancient Platonic feeling, albeit with a spooky modern twist. Thanks for watching.